Welcome to lecture 11. In this lecture, we will investigate the meaning of the geodesic equation that we derived in the last lecture. The geodesic equation takes the following form, which we found in the last lecture. It is the second time derivative of the coordinates x nu plus gamma nu alpha beta times dx alpha d tau dx beta d tau, where d tau is the proper time element. In this lecture, we're going to answer two questions. The first being, what does the geodesic equation actually mean physically? And the second question we're going to address is, how does one calculate these mysterious symbols that we just introduced as a shorthand notation in the last lecture? Let's get started. Get started by realizing that the proper time increment for particle d tau is given as the square root of minus the line element squared. Putting in the definition of the line element, we have that d tau is the square root of minus g mu dx mu dx mu. We can get the proper time for a particle traveling from A to B by integration. So the time that it takes from getting A and B in the particle's own rest frame is given by the integral from A to B times d tau. We can rewrite d tau using the expression that we found in equation 11.2. So we get this square root in here. And we can pull out the line element ds from this expression. So if you pull out a ds square under the square root, that gives us a ds in the integral. And that will be our measure for the integration. So basically, the integral turns into an integral from s at position A to s at position B times the integral over ds times this expression under the square root. So now recall that for Lagrangian mechanics, we found the equations of motions, EOM, by requiring that the action was minimal, so that the variation of the action was zero. We could try to do something like this by now taking the expression for a proper time for a particle traveling from A to B and minimizing the proper time. So requiring that the particle takes minimal time from position A to position B. So we'll hopefully get some equations of motion for the particle, and then we can study this. We proceed akin to our discussion of the equations of motion for the Lagrangians in an action. So we consider the coordinate variation x mu going over to x prime mu being x mu plus a small increment delta x mu. Because we're changing coordinates, and this change does not necessarily need to be a linear change in coordinates, our metric will also change or can potentially change. So we'll get a new metric g mu plus a small variation delta g mu. Of course, the variation in the metric is not independent from the variation or the change in coordinates. In fact, the change in the metric can be expressed as the derivative of the metric with respect to the coordinates times the change in the coordinates up to linear order. So now we want to take the expression for our proper time for a particle traveling from A to B, and we want to consider its variation to be zero, so the minimal time for the particle to take between these two positions A and B. So we're going to have the delta tau, the variation of the expression for tau is zero. So if we take the variation of the expression for the proper time tau from the last slide, the variation is that of the square root. The variation of the square root is 1 over twice the square root times the variation of the argument of the square root. And I've used the fact that the line element itself is invariant under coordinate transformations. So to simplify this expression, we can again note that this square root that we have here, we originally got by expressing d tau in terms of ds. So this square root here is nothing else but d tau by ds. So if we use that to simplify the expression, we find again that our expression for the minimal variation of the proper time is now given as 1/2 times the integral from time A to time B times d tau times dt squared over d tau squared times the variation of the argument of the action. For the variation of this argument, we want to calculate the variation of this thing here. So we get in principle 3 contributions. We get a contribution from the variation of the metric times these two terms unchanged. Plus we get a variation of the first entry, and we get a variation from the other coordinate x nu, just by following the chain rule. So we can regroup those a little bit. In particular, we can use the fact that the variation of the metric is nothing else but the derivative of the metric times a small variation times whatever we have in these parentheses here. And then the other two terms are just the same as in the line above. Now we can use this part of the measure ds squared over d tau squared. Let me go back here. This d tau squared over ds squared, and we can multiply it into the expression of this variation. That's useful because this variation here contains ds squared in the denominator for all of these three expressions, and we have a ds squared over d tau squared here in this part of the measure. So effectively, we can replace all d by ds in these variations here by d tau from this multiplying in this ds squared by d tau squared. So doing this, we find an expression that says that the minimum of the proper time is given if this integral here vanishes, and the integral here contains three terms, which are the three terms which we had on our previous slide. So now we want to integrate by parts to recast in particular these terms here that have the time derivative of the variation. We want to express it as the variation times the time derivative. There will be boundary terms, but these we neglect for the moment being, so we can think that these 2 points A and B are just infinitely far away. So then we can neglect the boundary terms. And we get, from rewriting this term, we get delta x mu times d by d tau of g mu nu dx nu by d tau. And for the second term, we get a similar expression, just exchanging nu and mu in the argument of whatever is being derived here. So that's the next step. So now what we do is we use the chain rule to express these derivatives d by d tau, once acting on the metric and once acting on the first derivative here. So we get two terms. So we have delta x mu g mu nu times a second derivative acting on nu, because the metric is symmetric. So then these two terms just contribute a factor of 2. And then we get two terms where the derivative is acting on the metric dg mu d tau with this part here, and the second contribution where the indices mu and nu are exchanged for these terms here. So finally, let's rewrite the derivative of the metric with respect to the proper time as the derivative of the metric with respect to coordinates times the change of the coordinates with respect to proper time. If we do this, then the above expression becomes the following. So the first line here is identical, and in the second line we now have terms that involve the derivative of the metric and two derivatives of the coordinates with respect to proper time. If we relabel indices so that the expression becomes slightly simpler, we find the following equation here. So we have a metric, second derivative of x nu with respect to time, and three terms that contain derivatives of coordinates with respect to proper time squared and derivatives of the metric. We can simply rewrite this again and write it in the following form, where now we have a second derivative with respect to the metric and collecting all terms that have two derivatives of coordinates with respect to proper time, and then we get some coefficient that is multiplying these two derivatives. Now we use the same idea as we did when we were deriving the equations of motion from a variation of the action. We say that the coordinate change delta x mu is arbitrary, so we can choose anything we want. We can choose a basis, and then each of these coefficients in the integration here has to be vanishing, And the only possibility for that is if the expression in brackets here is vanishing in order for the integral to evaluate to 0. So we get an equation of motion for the particle traveling from A to B to take minimum proper time, and that is given by the following equation here. We can get it in a form that is slightly more amenable to what we want to interpret by taking the contraction of this equation with respect to the inverse metric, g mu nu, or g mu sigma rather, such that this term here just gives us delta sigma, so this becomes a second derivative of x sigma. Then we have one expression that just contains the metric tensor and its derivative, and we have these two derivatives of the coordinates with respect to proper time. Now, of course, this is nothing else but our geodesic equation. This is a second order derivative of the coordinates with respect to time, two derivatives of coordinates with respect to proper time, and some coefficient in front. And the coefficient in front, by comparison with the geodesic equation, has to be our funny symbol gamma, sigma, alpha, beta. So basically, we can write these coefficients gamma, sigma, alpha, beta in terms of this combination of the metric and its derivatives. So let's now answer the two questions that we started posing ourselves at the beginning of this lecture. What does the geodesic equation mean? Well, by sort of deriving it in a different form in this lecture, we found that we get the geodesic equation as the equation of motion of a particle if that particle takes minimum time to travel from A to B. So it is, if you want, so the shortest path between 2 points. We also asked ourselves how we can calculate these mysterious coefficients gamma, sigma, alpha, beta, and we found that we can calculate them directly from the metric tensor, because the gamma can be or are calculated here from the metric tensor and derivatives of the metric tensor. These coefficients gamma, sigma, alpha, beta are variously called by different names. One name of them is connection coefficients, and the other one is Christoffel symbols. And we will calculate examples where we can evaluate these Christoffel symbols explicitly. We will start that next lecture. But the main message is that the geodesic equation essentially sort of replaces Newton's equation in flat space by an equation that tells you how or which path a particle will take if it takes minimum time from A to B. And we'll find that the common knowledge that the sort of minimum time for a particle to go from A to B is a straight line will change in gravity. So we'll get interesting sort of short path of shortest time to get from A to B from the geodesic equation. And that concludes the presentation.